Hi guys, can I get a sound check?
Yeah, I can hear you.
Okay, great. Thanks, guys.
Nice camera.
Thank you. I thought it was just too shameful, so I actually I decided to upgrade here. Actually, I pulled out my old GoPro. It turns out you can use it for webcam, which is cool. Okay.
Did I hear that right? You say you could use an old GoPro as a webcam?
Yeah, it's it's strictly speaking, it's not an old GoPro. It's a kind of it's a Hero 9, but you can use it as a webcam. I think you can use an older one too, but the new ones, I think the Hero 8, 9 and stuff, you can just use stock. Just plug it in.
Interesting. I have an old Hero 3 Black. I'll have to see if that works.
You might have to check out some YouTube or something on it to see I think there's some other software you might need. But for the new ones, there's you got to download something called the GoPro webcam, which is from GoPro. So, but yeah, it's awesome. Besides, like I said, I was like shameful for some. I'm in the image sensor business. It was sad to have a crappy camera. Okay. So sorry guys, my dogs are going nuts, or my dog actually has guests over, so it's just there might be some extra barking noises. Sorry about that. All right, let's see, what am I doing here? Oh, really? 5. Presented slides. Must be here. Okay, great. Okay, guys. So, so you guys are seeing my slide deck here. I mean, yeah. So, guys, like sometimes it's, I guess, it's the curse of being a teacher for me. That sometimes my lectures don't even make sense to myself, which I think was the case from Tuesday. So I thought I would like redo the example that we talked about. And I was trying to think of a real / fake scenario to step through all the stuff you might actually do in a lab or something like that to drive the point home. Okay, so this is going back to our example that you've got a cell phone, right? It's it wants some voltage in. Let's say it wants let's for a second section this discussion says say it wants 2 volts in. Cell phone wants And let's say you forgot you lost the charger. Okay. Now you've got like some circuit like that's outputting for the, again, this is like sort of, you want to build a circuit that creates a 2-volt output at the very least, if you give it some input, okay, some higher voltage input. So something that clamps on, sorry guys, let me see if I can close the door and try to reduce the dog noise. Sorry about that. So let's say now you want to, you're in the lab at Cal Poly, finally been allowed back on campus, and you're like, well, what do I do? And well, you know, like I remember from 2200 that if I have a bunch of forward bias diodes, if I have a diode, it kind of looks like, if it's forward biased, it looks like this, and the VD ons are typically 0.8 volts. Okay, so, well, if I have, you know, 3 of these, maybe I'll be able to get something like hooked up. Let's say, sorry, I guess you wanted a 2.4 volt, let's say. Okay, so you want to have a VD on of, you know, if I put 3 of these in series, I might have like a point. So I put 3 of these guys, I have them hooked up like this, and I have a V out. I'm gonna hook them up to ground so that, you know, I get basically, the idea is I'll get 0.8 volts here, 0.8 volts here, and 0.8 volts here, and I'll end up with 2.4 volts here if I have some V in. But wait a minute, because if I plug in V in directly here, I'm just shorting V in to V out. So I can't do that, because again, I can't have a direct short. It'll just V in will be equal to V out, and the whole thing will be shorted. So let me stick a resistor here. And I'm going to use a 100 ohm resistor, say here. Okay, and then I'm going to just, you know, in this circuit, V in is not directly connected to V out. V out is where you'll plug in your cell phone now, or whatever, let's say your cell phone, to see if this will charge. That's the idea of what you're thinking. Okay, I'm going to build this to replace this thing I lost. So does that make sense so far, the thinking behind this? I'd just go ahead and ask questions this time, because I'm like really trying to get the whole picture of like a sort of, again, a real scenario, maybe, or try to pretend like it's a real scenario. So jump in with questions. I don't have any other thing to do but go through this example in today's lecture. Although if we get done early, we could move on to some other stuff. Okay, so the first thing you do is you go, okay, well, let me do this. Look at it on with pen and paper. Do a really simple model and see if this roughly does do what I'm looking for. Because, you know, I added this 100 ohm resistor and so on. So let's see, what does it do? So the first thing you can do is, as a real simple approximation, right? Simple model. Which I should say simple analysis, right? You want to do this, you want to do a real 5-minute analysis just to see if this circuit does roughly what you want to do. Okay, so for this real simple analysis, you would go, okay, let me just use this model for the diode. Okay, this is called the constant voltage model. Okay, and the way it works is if my Vn is very negative, Okay, this end of the circuit is going to go below ground. So this guy's going to go way below ground. And all these guys are going to be reverse biased. So I remember in the curse of, for a reverse bias diode, meaning that it looks like this side is more negative than this side, then the diode is going to look like a open circuit. So I'm going to redraw my circuit. I have a resistor. So I have Vn and I have V out. And I have, I'll put the battery in, so it looks like a battery, but it doesn't matter because they're all going to be open anyway. Oops. So all of them open. Okay, so in this case, Vn, so we got all this, this is just have open circuits all the way going down here. And there's no current flowing from Vn to V out. So V out, but there is a connection from Vn to V out through the resistor, right? But there's no current flowing because there's no current to go, you're not having any current going down here. So I'm assuming that the current in your, through your cell phone is going to be small in this example. Okay. So for this case, V out is just going to equal to V in. Right, because there's no resistive. So the way, if you want to do a KVL, V out is equal to V in plus IR, and I is equal to 0, so V out is just equal to V in. Okay, so that's in the very negative case. Then we look at also the very positive case. So in that case, I'm going to guarantee that I'm going to really put a big voltage here. So I'm going to be in forward bias. Meaning that my diodes are going to have a higher voltage here than here. Okay. And so what it's going to look like is this. So I'm going to redraw my circuit. Okay, so now in this case, this gets a little confusing because in this case you have like basically 3 batteries in series hooked up to your output, 2.4 volts. Okay, and you've got a resistor hooked up to this. Whenever you see a battery or a voltage source connected to a node, it wins the fight. If something else is trying to change that voltage somehow, the battery or voltage source is going to win because it has lower resistance. It has infinitely low resistance, or it has 0 resistance. So whenever you have a situation like this, this guy wins. And so V out is just equal to 2.4 volts because it looks like it's just shorted to this battery made out of 3 batteries, each one being 0.8 volts, sorry. So it's 2.4 volts, okay? And so that's what happens in the extremes of negative voltage and extremes of positive voltage. And if you want to see where the break-even point is, you get, you say, well, I'm going to make this equal to this and see where the break-even is. So Vn is equal to V out is equal to 2.4 volts, means that Vn is equal to 2.4 volts. That's where it breaks sort of the break-even places. So if I was going to plot this, right, if I was going to plot V in and V out, what I would have is when I'm very negative, so out here, when I'm very negative, V in is just equal to V out. Okay, so if I was going to plot it, let's say I'm going to plot it below zero. So the n is just a oops, sorry, that should be a straight line. And the slope of it is 1. Okay, and then that's going to happen until the n is 2.4 volts. So out here somewhere, 2.4 volts, and oops, and V out is V out is 2.4 volts. I'm sorry, guys. Let me close one more door. Hold that. You guys have to really right now. I need your help. I need your help. Come on, come on. Acted up here. All right, guys, so it'll look like that. Okay, so it'll just follow the output, will just follow the input until the input's at 2.4 volts, and then it's just gonna clamp at 2.4 volts. Okay, any questions about that? What we just did? So what would happen is if, like, let's say Vn is 1 volt, okay, then these diodes are going to be off. So if it's 1 volt here, these guys are going to be off. There's no current flowing through here, so V out is just going to be 1 volt. If Vn is 1.5 volts, these guys are still off, and V out is just going to be 1.5 volts. As soon as Vn becomes 2.4 volts, though, all of a sudden these guys are going to turn on, and V out is just going to peg to 2.4. Okay, and it's just going to stay that way. And then, so Vn can be like 100 volts, and V out is going to stay at 2.4 volts. Okay, and the difference in that voltage, let's say for the sake of discussion, Vn is at 5 volts, and V out is 2.4 volts. It's going to drop across this resistor. So that whatever that is, that whatever 2.6 volts is going to drop across this resistor. If you go to 6 volts, it'll be 3.6 volts, etc. But V out is just going to get clamped to 2.4 volts. Any questions about that?
Kind of. How does different like input voltages change the look of our graph?
I'm sorry?
We're talking how does different input voltages for like Vn and or V out change the look of our graph?
So here, if you have different VNs, what it's telling you is you're sweeping your VN, and as long as VN is below 2.4 volts, it's saying V out is just going to follow VN. That means if VN is minus 10 volts, V out is going to be minus 10 volts. Okay, right until you hit Vn of 2.4 volts, and then it's going to peg. So as long as you got this circuit, you can just sweep the input around all you want, and you're going to get this relationship between input and output. Okay. Okay, so now let's say you actually go and implement this circuit. So let me show you guys. I made a share screen. Wait, did you have a question? If I put voltage V1, it would be just divided into 3 batteries. That was pretty much fixed then. So if you put in a different voltage V1, if you like, basically this is saying it's not gonna change V out. So V in, so once the batteries turn on, that's it. They're gonna be at 2.4 volts. Okay, okay, so I think you got the answer, gotcha, okay. So let's say, so let me see, I'm trying to share you guys. Want to continue. Okay. Share. Okay, so I don't know if you guys are familiar, there's a computer aided simulation tool for circuits. I don't know if you guys have heard of it or not. It's called SPICE, S-P-I-C-E. So what I did was I said, okay, I'm gonna pretend, I'm gonna use that because, we're not in the lab now, to pretend like you're in the lab and you actually put this circuit together. Okay, so I'm going to use that as if it's like a live thing in the lab. So I went and got these diodes from somewhere, from the store. I don't know which store sells diodes. And I hooked them up to a 100 ohm resistor, and now I've got a voltage supply in the lab, and I'm going to put my multimeter here, out here, and see what happens. Everybody see that? Okay, so the diodes I got were these things 1N914. Okay, so these are just diodes that were available. I picked them off, sort of a random place. So let me now share the output, which is where. Did that change anything? No. Let's see. Share. Did that do anything, guys? No. You see something else, or is it
We
still?
see your graph. Is that what you want us to see?
Yep, that's the graph. Okay, good. So zoom to fit. Let me kill this. I was playing around with this. Okay, so now, whoops, what happened? Sorry guys, I got all these different windows and stuff. Okay, so now when I actually plug this in, okay, when I actually plug it in, I get this graph, which kind of looks right. It's like this is kind of in the negative territory. So V out, so this is, I'm sorry guys, I didn't describe the graph. So this is, I'm plotting V in and I'm plotting V out. Okay, so I basically, let's just pretend we went into the lab, made the circuit, and we're just plotting, we're sweeping V in and looking at the V out. Okay, so here V in is equal to V out. So let's say we take this point, whatever, roughly these points, V in is equal to V out. Okay, and then it goes high, 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 high. It does clip, but the point that it clips at looks like it's not really 2.4 volts. It's like 2 volts, and you don't immediately go to 2.4 volts, right? It just kind of does this thing. It's not a sharp step, okay? But it kind of looks roughly right, okay? And so this is the limitation of our constant voltage model, okay? So notice asymptotically in the end here, like, do you guys see my cursor?
Yeah, we can see it.
So out here, it's correct. It's 2.4 voltage. It's 2.3, 2 point whatever it is, 2.6, whatever it is. Out here, it's correct, but here, it's kind of correct more or less, but it's not exactly the graph we drew. And that is the limitation of that constant voltage model. It gives you this rough graph, but right around the inflection point, the diode isn't exactly a constant voltage model. It's this exponential model. So you go, well, okay, let me see then if I did this circuit right. So you remember that. You go, okay, so start broadcast. You go, well, okay, that's not quite right. So let me see if my
Is it the screen's still supposed to be the
yeah, let me try to get back to my screen. So now you go, like if I try to read, it's not going to be exactly the graph, but it's if I was going to draw what we just saw, it kind of looked like this or something. All right, so you go, let me see. Oh yeah, I remember that this VD this model that we've got that is either, whoops, it's either an on or an off switch with a VD on of 0.8. This is just a simple model. So in real life, sometimes you just stop right there and you go, that's good enough. You know, it kind of roughly does what I want. I'm good to go. And sometimes you go, that might be a little shaky, or let's say you're doing this for your manager on the job or something, or you want to make sure this works with under all conditions, or your cell phone is particularly precious to you, so you're a little bit worried to plug it into something you don't quite understand. And then this is when you go, okay, I want to dig into what's going on here, so let me plug in my actual model. ID is equal to I sub s exponential of VD over VT. Okay, so this is the actual model. So let me actually plug this in and see if I get any closer to what I'm measuring. So fine. So the first thing though you got to do is to find out what IS is, right? So I'm going to go and look up the diode that I got. Let's see. Safari. Okay, so you guys should see my Safari screen. Okay, so this is the diode that I got. Okay, it's I don't know if you guys remember from my screen, it's whatever 1N914. Okay, which is what was available. I bought it, and it has this data here. Okay, blah 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 blah. But what I really want to get is I sub s. Okay. Notice, for the sake of discussion, let's say I got this particular model. There's a bunch of different models. Okay, there's a bunch of 916B, but I got the 914B, let's say. Okay, so I got that model. So I don't quite see what I need to get I sub s. So let me try to see if I can figure it out from this number. They're telling me if the forward current is 5 milliamps, the voltage, the VD on of the diode is going to be 0.62 to 0.72. Okay, so right off the bat, it's telling me, look, that 0.8 volts I used as a simple model. It's not always correct. It just depends on how much current's going through the diode, depends on the particulars of the diode, and so on. So let me just use this to try to figure out if I, what I sub s should be. Okay. So one good thing to notice on the spec sheet is that this is a manufactured part. No manufactured part is without some level of tolerance. Okay. So you're not going to buy a part that's going to always have all the specs are going to be the same. Notice that there is a pretty big variation already between 0.62 and 0.72. That means that your I sub s, okay, so remember the equation for the current, I'll write this down again. or we'll go back to that screen, is I sub D, which is this 5 milliamps, is equal to I sub S natural log of VD over VT. VT is a physical constant. It's not going to change. Okay. So if VD is changing by 100 millivolts here, means I sub S has changed quite a bit, meaning that that's the tolerance of the manufacturing process. When you go buy a diode, some diodes might have a certain I sub S, and some other diodes might have a different I sub S's. There's just a range of them, and you should be prepared to deal with that. Okay, so in your designs, okay, and again in the real world. Okay, so let's go back to my shared screen. Okay, so again, I'm just going to replicate. Oops, am I sharing? No, I'm not sharing. You guys aren't seeing my.
Yeah, we still see the like data sheet.
Okay. Okay, so let me just replicate those two things. So it said that the I forward by current of 5 milliamps gave either a minimum forward voltage, so that would be VD in our language. It called it V sub F, forward voltage. It's the same thing. So it gave a 0.62 volts and a max of 0.72 volts. And again, if you look at this equation, if I sub D is constant, which is this, V sub T is I'm saying it's a physical constant at a particular temperature, means that the only way you could get this range of VDs is if I sub S is changing from part to part. Okay, and this is the range of tolerances available. Okay, so for our better model, let's just do the average value, right? So if they're saying this gives a certain I sub S, so this gives you I sub S min, say, and this gives you I sub S max. Let me try to come up with an I sub S nominal, an average I sub S. Okay, so I'm just gonna do like a dumbass thing and just average these two. So plus 0.72 divided by 2 gives me 0.67 volts. So I'm hoping that, my average I sub S is gonna be 4.67 volts. So it's gonna, for a forward bias of forward current of 5 milliamps, it's going to give this, so I can back calculate I sub S. So I can go back to this. I'm going to rewrite that as I sub S is I sub D over exponential of VD over VT. I'm going to get 5 milliamps is what the spec sheet said. Exponential of 0.67 over volts, 0.67 volts divided by 26 millivolts. So I'm doing this just to be able to, because the data sheet didn't give me I sub S directly. I'm just trying to calculate I sub S. Okay, so from this I get 3.2, roughly 3.2 times 10 to the minus 14 amps. Okay, so this is my I sub S. Now I'm gonna go through and try to figure out, well, what's my voltage? So this is the better model, right? So the simpler model told me at 2.4 volts VN, I'm going to have 2.4 volts. And let's say furthermore, I expect to be sort of at 3 volts. That's where I expect to be. So I'm going to calculate what my voltage should be at 3 volts. The simple model told me at 3 volts, I'll be at 2.4 volts output. Let's see what I'll really be. So now more accurate calculation. Okay, so now I basically say, okay, so I have 3 volts here. I still have my 100 ohm resistor, and I've got these 3 diodes. Okay, so let's say I am gonna start with the assumption, I'm still gonna start with the assumption of 0.8 volts per diode, right? That's gonna be my first step. So this is the iterative model of trying to come up with a more accurate value for what happens, okay, which is a lot more painful, it's a lot more time consuming, but should be more accurate, okay? So the first thing is we come up with that. This gives us our first estimate at V out. This is V out is 2.4 volts, right? So that's 0.8 times 3. Okay, so my I sub X, which is the same as the current going through these guys, is going to be 3 volts minus 2.4 volts divided by 100 ohms. So that is going to be 6 milliamps. Okay, then I plug it back into the model. So now I'm going to see if this value gives my VD of 0.8 volts. So VD is equal to, so VT natural log of ID over I sub S. This equation I just wrote is the same as my model. I'm just rewriting it so that it's in terms of VD. Okay, so I just rewrote it in terms of this. So this is 26 millivolts times natural log of 6 milliamps over the I sub S that I think I have for this diode. Okay, so this gives me 0.675 volts per diode. And it's like, oops, this is pretty big difference between this and my assumption of 0.8 volts. So it's already telling me like, oh, like my simple model is off right there. My VD on at this value wasn't quite right. But remember, this is an iterative procedure because I calculated I sub X based on an initial gate of 0.8. If that 0.8 value was incorrect, my I sub X would also be incorrect. So I got to plug this back in and do a second iteration. So this is the problem with this analysis. So the second estimate for I sub X is at V out of 3 times 0.675 volts, which is 2.02 volts, which is pretty different than 2.4 volts that my simple model was telling me. Okay, so now again, this is my second iteration. So I'm going to calculate I sub X again. It's 3 volts minus 2.02 volts divided by 100 ohms. And now I get 9.8 milliamps. Okay, so I'm going to plug this in again. So VD is VT, natural log of 9.8 milliamps, 3.2 times 10 to the minus 14 amps is equal to 0.6875. So this iteration gave me a value pretty close to that. So it means that I'm getting pretty close. you guys might want to stop here. It's your call, or if you really want even a more accurate value, you can go through another iteration. So plug it in again. So third estimate. Notice that it's taken me how much longer this has taken me to calculate than just this simple model where we were at, right? This was pretty quick. I didn't even need a calculator. I just sort of like come up with some simple procedure and gave this plot. Now I'm like, plugging in, figuring out natural log values, etc. So now a V out of 2.06 volts. So this is 3 times 0.6875 volts. Now my I sub x is 3 volts minus 2.06 volts divided by 100 ohms is 9.4 milliamps. Then I calculate VD again. And I get 6.6865. So I can just keep going. Notice I'm like, this is a numerical method. I'm going to converge to a value as I keep making estimates. But at this point, I'm going to say it's close enough. This value of my third estimate is within like, I don't know, like a millivolt of my last value. That's good enough. Okay, so I'm going to call it this. Okay, so that's my hand calculation. So this gives me a V out of 3 times 0.6865 volts, or 2.06 volts at a V in of 3 volts. Okay, so I'm going to go back to my bench top, and I am going to look at, okay, so I'm going back to this plot. Okay, so you guys are seeing the plot. Okay, so I'm going to go kind of zoom in here. Where was I? 3 volts. Blah, blah, right there. There you go. So I calculated 2.06, and my actual lab results or whatever shows 2.055. So I was within a 10 millivolt now of my estimate, the more accurate model. Okay, but it took me a lot longer to get here. But now it's telling me like, hey, right where you want it to be isn't, that's, it's kind of like, it's a little shaky there. It's like, giving you a value of 2 volts, 2.06 volts, where you expect a 2.4. So it depends on your application in reality about where you want to be, etc. Okay, so does this, I'm hoping this clarifies to you guys the difference between the different models we're using here. We've got the quick and dirty model for the constant voltage, or the ideal model would be even more off, but easier to apply. So, but you can see how it got you kind of roughly the right curve. It got you the right curve, shape of the curve. It puts you roughly at the right values, but not quite. To get more accurate, we needed to use the more accurate model for where we were at. Okay, so that's the difference between, but then also it took us a lot longer to get there. Right? We have to do this iterative procedure and so on. Okay, now let's say that I'm going to go, okay, well, that was at 3 volts. What would happen at 3.5 volts, right? That 3 volts didn't quite get me to where I wanted. Let me see if I plug in 3.5 volts, what would happen, right? What would that tell me? So I'm gonna go, I'm not gonna do this to you guys, but what you would have to do is
We only see the graph right now.
still, okay. Okay, so I'm not gonna do this to you guys, but if I wanted to figure out what the heck was gonna happen, and so now I realize with the 3 diodes, with at least these diodes that I bought, I'm not getting to the 2.4 volts I needed for my cell phone. So I'm gonna see if if I crank up this 3 volts to 3.5, will it get me there? Let me do this. So if I was gonna try to figure that out, I would have to do this procedure over again, but this time with a VN of 3.5 and start doing this calculations again. Okay. Okay, so this brings us to our next model, which was the small signal model, which is again another simplification. What I'm trying to show you guys is that this model, this exponential model, is pretty accurate given that you have a good value I sub s and so on, but it's tedious to use in the sense that, and just remember, we've got 3 diodes and 1 resistor in our circuit, and the diodes are all connected the same way. This is as simple a circuit as you can possibly get, and it's pretty tedious to go through it. So what we're doing is we're going to go, when we can, we want to use the simple model. When it doesn't quite work, we have to go back to this more complicated model, which actually gives us a pretty good, the complicated model gives us a pretty good answer. Okay. But so the second simplifying model that we have is a small signal model. Okay. So, and that's just as a reminder of what that looks like is, it says, so VD, I sub D, so this is my complicated model, right? It says I sub D is, this is in the forward bias, exponential of VD over VT, and here is minus I sub S, and out here, intermediate, it's the full model, which is I sub S exponential of VD over VT minus 1. Okay, so the small signal model says, and in this particular set, and then remember, this is the voltage across one diode. Okay, so in this case, it's we know it's 0.685 and 9.4 milliamps. So if I was going to, let's say I plot this particular case, so I would be here, 9.4 milliamps and a 0.6865 volts. Okay, so it gives me this point on this exponential curve. What this small signal model says is if I'm right around this point, okay, if I'm right around this point, not over here, not over here, not too far away. So let's say if I'm at point, the diode is sort of around here somewhere. Let's say this is 0.68565 volts plus, I don't know, what's a good number? Plus 25 millivolts. I just made that up. Okay, a small number. So a small region around my actually calculated value. I can estimate this point as if this difference is like a resistor. Okay, that's the small signal model. Then I'm going to zoom in here, zoom in here, and just for this range, I'm going to draw like a straight line between these 2 points and pretend like my diode, just for the difference though. Remember, this is just for the difference from here to here. So just the difference in current and in voltage from here to here. Just for that difference, I'm going to pretend like this is a resistor with a resistance of I sub D over V sub T. No, sorry, V sub T over I sub D. I always get this wrong. V sub T over I sub D, where I sub D is this guy. Okay, and V sub T is our constant, 26 millivolts. Okay, so, and I just remember, this is just for the difference, meaning that my circuit really looks like if I had a diode. So, well, let me actually draw it for you guys. So meaning that my real circuit let's say I wanted to see what this was doing as 3.5 volts. Okay, so I'm dividing this circuit into 2 circuits. Okay, again, for simple analysis. I already have a calculation at 3 volts. So that's going to look like that. That gave me 2.06 volts on the output, and the delta, the VD across each one of these guys was 0.6865 volts. It's going to look like, so that's what it's called, my bias point calculation or large signal model. Okay, and then I'm going to pretend like the rest of it is all the changes I want. So this is this other model that I'm going to superimpose on this is just all the deltas. So I'm going to have the delta V of 0.5 volts. And my resistor is going to say the resistor. And then instead of the diodes, I'm going to have these this linear model of the diode, which is just looks like a bunch of resistors at a V sub T over I sub D, V sub T over I sub D, V sub T over I sub D. Okay, and so what is this value? What is this value? Well, it's just R sub D is just, again, it's just at this point. Just at that point, I'm going to use this 9.4 milliamps for my I sub D. So it's going to be V sub T over 9.4 milliamps, which is 26 millivolts over 9.4 milliamps, which gives me 2.766 ohms. Okay, so 2.766 ohms. Sorry, guys, So let me redraw this. It's going to look like So in sum, this is what, 8.29 ohms. Okay. Now this just now looks like a voltage divider. Okay, so if I just do that, my V out, my delta V out is gonna be 8.29 ohms over 8.29 ohms plus 100 ohms times 0.5 volts. Or 38 millivolts. Okay, so this tells me that my delta, so that tells me my V out, sorry, my V out at V in of 3.5 volts is going to be what I had, this guy times 3. So that was 2.06 volts. Okay, everybody see what I did there? So I could have, if I wanted, so this is what it tells me I would be if I was at this higher value, okay, of 2.5. So I could have gone and changed again. I could have gone and put this guy at 3.5 volt and we did all these sort of my exponential and natural law calculations, or I made this small signal model for the diode just in this small range around my previous calculation, which I'm calling my bias point, and just added, just pretended like it was a resistor, and I got this 2.08 volts. Okay, so now let me go back to my curve. I'm going to zoom in. So 3.5 volts.
It's still not close.
2.5, getting close. Thought I did these numbers. No, it's so we calculated 2.098 volts, and we're getting 2.1 volts. So you see how the calculation ended up being like close to reality. So it just tells you it's still not close, like you're saying, but instead of doing another exponential natural law calculation, all I did like was a resistive calculation and I got close to the real value. Does this make sense to you guys? So all this is telling me in the end that, like, hey, this approach we've got with this particular diode isn't gonna get you like to 2.4 really easily. Until you get to really high voltages, maybe you should consider having like a fourth diode or something there. Okay, but so these are the simplifying models that we're using. We've got our the true model is this exponential diode model. The one simplifying approach in one direction is this constant voltage model or ideal model for a diode that gives you really rough values. And on the other side, if you have one value, one bias point calculated for your diode, and you make a small change around that, you can use your small signal model to sort of get a new pretty good estimate on what's going to happen. Okay, so this, I don't know if you guys are kind of like sort of catching on to where we're going in this class. It's philosophically, it's a little weird because a lot of times what you're doing in your classes is, you know, you're let's say you're studying one physics concept, right? You're studying like electromagnetics. And the further you delve into electromagnetics, you're getting into more and more complex models, more and more complex analysis. You're digging into the details as you're getting more advanced to get a, you know, better understanding. What happens in microelectronics is kind of a little bit different. What we're teaching you in this class is how to use simplifying models to analyze your circuits relatively quickly. Okay, still as it's taken a lot of time, etc. But in fact, instead of teaching you how, you know, delving into the diode model and saying, well, the exponential has other factors, etc., we're saying, you know, let's see how we can get rid of this exponential. Let's use a piecewise linear model for this kind of analysis. And let's just pretend like that exponential is a linear model when you only have a small value. So it's sort of going the other way. It's simplifying the model, although you always have to understand how, you know, are you using the right assumptions to be able to simplify, but using those simplifying models to be able to design complex circuits. Because again, this is like the simplest thing you could possibly imagine, right? A resistor and 3 diodes, a resistor and a diode, whatever. In real life, the circuits get really complicated. So you want to have these simplifying models, but you got to know when you can use them and when you can't, and what the limitations are on these models. Okay, so that's kind of the philosophy of where we're going. And we're doing that for the diode, okay, which has these simplifying models. Then we're going to get to the transistors, and they're going to be similar. Transistors, we're going to talk a little bit about what the device looks like. And then we're going to talk about how to simplify the model so you can actually use it for designs. Any questions about that whole thing? I was hoping to sort of build this scenario so you guys have like a general idea, the lay of the land of why we're doing what we're doing, and what the different procedures look like and how they relate to each other.
Yeah, I really appreciate the use of like the real world examples. I truly believe that kind of helps paint the picture of like what we're actually doing.
Okay.
Yeah, like this example and stuff was much better.
Okay, great. I'm happy about that. Okay, sounds great, guys. And then so one last thing I want to tell you guys. So so this also like begs the question, why do any hand analysis at all, right? I went to this, I pretended like my real life was this spice model, right? So whenever I want to design something, just plug in stuff into Spice and simulate. Why even do any hand analysis? Okay, and this question comes up all the time. It even comes up in my mind, and it goes into every designer's mind, even at work, even several years into your work. Your temptation is to throw everything into your simulation tool and start simulating and start tweaking stuff, values here and there until you get the value you want. And then you go, okay, that's my design. Which is like a very tempting to do, but it's a very typically a rookie mistake. The reason is, again, the circuits are really complicated. You might have 30 transistors in the circuit you're trying to design. Okay, let's say you have 30 transistors and you have 50 resistors. And you throw them all in there in your simulation tool, you simulate it, and you get something. You get something and it looks like kind of like what you want. Okay, you go, great. That was good. I don't need handle analysis. I don't need to analyze this. I just use the spice model. But the problem is in real life, when you try to produce that part over and over again, you'll have variations on those transistor values. You'll have variation on the resistor values. You'll have variations of temperature, so on and so forth. So if you do not have a idea about how the circuit works without using the computer-aided design tool, you're going to be nowhere. You're going to build circuits that are going to fail in production, or you're going to build something, go to a design review, right? Basically, you're showing your design to the management, etc., and get torn to shreds because they're going to ask you, hey, like, what if this changes? What if that changes? And like all you can say is, look, I simulated it and it worked under this condition, but nobody's going to take a chance of building this what you made in production without understanding fundamentally how the circuit works. So that's why we study these hand analysis, hand estimate of the circuits. And what you really want to do is the same procedures we just talked about. What you do is you use the simplest model in your head. Like, again, this is like hour one of when you're assigned to design something at work. Hour one is you're just sketching something out using really rough models like the constant voltage model or something. Is this roughly going to get me to where I want to go? Okay, yes, no. If no, then you keep iterating your circuit idea, or trying to going and seeing what circuit might work and working it out. If it looks like it's going to work roughly, then the next step you do is you do some rough calculations, and that'll be our second level of simplified model, which are like the small signal model, etc., and figure out, is this in a more detailed way, does it get me to where I want to go? That'll be like hour two. And if all that looks good fundamentally, then hour three, you start plugging into your SPICE simulator and simulating around and making sure your hand calculations were correct. Because at that point, you also know what the dependencies are. So when you're simulating and something looks a little off, you know what to adjust, because you have a feel for what your circuit's doing. Okay, so that's the reality of good design. Of course, the hour 1, 2, 3 might be like week 1, week 2, week 3, depending on how complex your circuit is. Maybe it'll be month 1, month 2, month 3. I don't know, but it just depends on what you're designing. Okay, so that's where we are, guys. Any other questions? If you guys aren't familiar with SPICE, I keep thinking about putting some level of SPICE work into this lab of using this tool, because like it'll be something that you guys will be using in your career. But anyway, I haven't done that, but if you do want to play around with it, it's never too early to learn how to use the tool. I've used it for like I've been using SPICE for like 32 years or something, some crazy number of years.
LT Spice, correct?
Yeah, well, I use, so LT Spice is a free, it's like shareware, and it works on both Mac and PC. So I like it. That's why I use it. And I haven't figured out anything that it can't do yet. I know like some of you guys, a lot of you guys, or a lot of the students at Cal Poly use PSpice. That also works. The engine behind the tool is the same engine. It's basically spice it's like a simultaneous differential equation calculator for a whole bunch of circuit nodes, etc. So the engine is always sort of pretty much the same. They might converge faster or run faster or slower, or whatever, but sort of that front works. So I like LT Spice just because it's free and it works on. I use Macs, and so that's why I like it.
Easier to use than PSpice.
What's that?
And I think it's easier to use than PSpice,
Yeah.
in my opinion. Could you maybe go back to the other, or to your other slide where you were writing?
Sure. Hold on a second. Which which page?
This like bias point calculator. Can you
Which one?
up a little bit? Yeah, there where you kind of broke off into two different graphs and it says bias point calculator. Can you explain that? And
Sure.
is that like
Yeah.
relevant to the right side that you started graphing, or
Yeah.
is that
Yeah. So the small signal model can't stand by itself. By definition, the small signal model is sort of a differential model, let's say. I don't know what word to use. It's only referring a new point to a previously close point. Okay. So if I was just trying to figure out I sub D, and I use this resistive equation, just, if I plugged it in with this, without realizing that this is only representing the step from here, this point to this point, then it would give me some really weird value. Okay, so what I have to do is remember that I am superimposing this resistor, this resistive value on my starting point, which is my starting point is my bias point, which I used the full model to calculate. Okay, that's for a small signal model, that's my starting point. And the small signal model only tells me if I go a small step up or down from that model, what happens. Not if I forget that I'm starting from here and going up or down, then I'll end up here and go up and down, and it's just gotta get a nonsensical answer. So the idea behind the small signal model is you need to remember that you're making a small change around a bias point. So this is your bias point, and you're going a small value around that. And that's how this simplifying model works. It can't stand by itself. It's a variation around a bias point, a major. So it's basically this resistor only makes sense as a small variation around this. Does that make sense?
Yeah, it does.
So it's really easy to forget to do that, but just have to remember that the only way I can use the small signal model is I'm starting at this point and using it as like my guidance, let's say. And I'm only saying, well, what would happen if I have a small change right around this point? Small change up or down, depending on what you want to do. But for example, again, if I was, let's say, if my bias point was here, like this bias point will not tell me anything about what happens out here or what happens out here. So I always have to if I want to know where I am here, it has to be this point plus the small signal value.
Okay.
Not just the small signal.
So it looks like for the small signal value, you just need to find your RD and your change in V.
Exactly. But, and just, exactly, just the small signal is only looking at the changes. So that's why I'm only looking at delta V. And this R sub D only tells me the change in the voltage of that.
And it looks like we used some of the values from the prior calculations for the small signal model. So we would have to do those like calculations from the exponential or to use the small signal model or no?
Yeah, yeah. So what you always have to do to be able to use the small signal model is you calculate a bias point. You use that as your starting point. You have to use your full up model to calculate that center point or bias point. And then from there on, you can use the small signal model to figure out what happens around it.
Cool.
So you still have the work of figuring out this bias point. What you've saved yourself is figuring out the bias, using that exponential or natural log model to figuring out all these points in between. That's the work you've saved yourself. And it turns, sorry, go ahead.
No, I was just saying cool and sweet.
Yeah, and it just turns out, fortunately, or I gotta think about the philosophy of this, if that's how the world works, or that's how we got, people built analog circuits, but most analog circuits operate in this way, where you have very small signals that your inputs are not like huge transitions. You're actually either your instruments or whatever you're dealing with, it has a very small input, or you're sort of creating a situation where you're dealing with a small input. So it's not an unrealistic scenario to be able to use the small signal model most of the time in analog circuits. So it works, it's like extremely useful tool.
Cool.
Okay, guys, any other questions?
Why did you choose 3.5 volts again?
Why did I use 3.5? I was just trying to show you guys what happens when there's a variation. So
Okay.
that's the real reason, but like sort of the conceit of this made up problem was you were trying to see if I crank up like at 3 volts, you didn't get 2.4 volts. So you go, gee, what if I crank up the voltage from 3 volts to 3.5? Will that take me from 2 to 2.4 or what? So that was sort of the conceit of the problem. Does that make sense?
Yes.
So I was just trying to like show you guys that, if you're around that initial point and you're making a small change, what happens? Anything else, guys? Like Brandon doesn't like P-Spice. No, I don't like P-Spice either. I don't blame him. All right, guys. Okay, so I'll let you guys go. Homework set 2 solutions are up. Again, that's like, I'm sorry, but that's this nature of the beast. It just helps to do a lot of problems, work through your problems. All right, guys, have a good weekend.
Thank you, Professor.
Thanks. Take care.
Bye.
Bye.
Thank you.
Thanks.